Thanks. I'll begin. Dear Father, we thank you for this day. Again, Lord, thank you for the students. Just pray you'd help us to use this time wisely, Lord, to glorify you and what we do, Lord. In your name I pray. Amen. All right, so I got through a lot of things yesterday, but didn't get to this one. So I thought we should start with this. Verify the divergence theorem for this vector field on the sphere. So I've called B the ball. So what's the boundary of B? That would just be x, y, z such that what? X squared plus y squared plus z squared equals to 1. Oftentimes, if you've got some solid region defined by an inequality, a lot of times you can just take the equality to define the boundary. There's probably some example out there which violates this principle, but it's often true. So that's the sphere. That's the ball, let's say. And the divergence theorem alleges that the flux through the boundary of the ball of f dot ds is equal to the triple integral through the ball of the divergence of f over the volume. So we need to calculate both of these things. I'm going to call this 2, and I'm going to call this 1 because I feel like 1 is more restful to start with. All right. 2 is going to hurt a little bit. 1 should be a piece of cake, though, I think. So 1, to calculate, we need the divergence, right? What's the divergence of f here? So we just got ourselves a z squared, I think, right? So the divergence of f is z squared. There is no, the x and y terms both differentiate to 0, right? So the divergence isn't too bad. And we wish to integrate over, well, if you look at what it is, over b, which is simply 0 less than or equal to rho less than or equal to 1, 0 less than or equal to theta less than or equal to 2 pi, 0 less than or equal to phi less than or equal to pi. And may I recommend that we use spherical coordinates to calculate the spherical integral. And also we should recall that the dv, the volume element in sphericals, is rho squared sine phi d phi d theta the differentials. Whatever order makes sense for the integration I'm about to write down. Now I have to remember that off the top of my head because I'm too lazy to get a piece of paper to look at. But you guys have this thing called a 3x5 card for the test, so, you know, yay. So there's that. Just saying that's definitely one of those things that ought to be on that card, right? Because if you don't know the spherical volume element and you kind of try to go do a spherical integral, that could be very bad. A lot of times I engineer a problem so that if you do it correctly, the calculation is nice. But if you were to, say, not do it nicely, say if you were to be foolish and say that dv was just, I don't know, d rho, d theta, d phi, then all of a sudden integral which you can do becomes integral you can't do. And, well, anyway, it's integration. It's fragile. It's easy to break it, all right? In the sense of it's easy to make a hard problem, excuse me, an easy problem into a hard problem is what my point was. Okay, so here we go. Enough jibber jabber, to quote the venerable Mr. T. Let's see here, so integral from 0 to 1, integral from 0 to pi, let's say, integral from 0 to 2 pi, why not? And then my z squared. What is z squared? Well, z squared is rho squared cosine squared phi. Yes, no? And so we got is a rho to the 4th. Got myself a cosine squared phi, sine phi. Now be careful. since I wrote these down, I'm stuck with d theta, d phi, d rho. All right. Let's see here. So you've got this and that. So I get integral from 0 to 1 of rho to the 4th d rho, integral from 0 to 2 pi of d theta, and finally integral from 0 to pi of cosine squared phi sine phi d phi. The cool thing about a sphere is that in spherical coordinates, the bounds are rectangular in the sense that they're not variable bounds, right? Which means that sometimes the calculation really does simplify quite a bit. If we were using Cartesian coordinates right now, this would be so much worse, right? We'd have to do like integral from -1 to 1 for x, integral from minus the square root of 1 minus x squared to 1 minus y squared for the y, and the integral from like minus the square root of 1 minus x squared minus y squared to the square root of 1 minus x squared minus y squared for z. It's just horrible. Look at how much nicer this is. All right, I shut up. So, yeah?
I was just wondering, because you always say it's a lot easier with the spherical coordinates.
Yeah.
Is one of the main reasons other coordinate systems were made was to help make integrals of these problems easier?
So your question is, did we invent like new coordinate systems just for the sake of doing integration?
Is that one of the reasons?
It's definitely one of the reasons that they've been popularized, I think, yeah.
Okay.
There are other good reasons in physics. If you study, for example, Lagrangian mechanics, what you learn is that the Euler Lagrange equations can be stated like this: d dt of partial L partial q dot equals to partial L partial q. These are the so-called Euler Lagrange equations of classical mechanics. And these equations make sense for q being what's called a generalized coordinate. So yeah, q could be like a linear coordinate like we're used to, like x, y, z. But you know what? Q could also be a radial coordinate, or a theta, or a rho, or a phi. And the equations of physics still make sense with respect to those generalized coordinate systems. This is the genius of Lagrange. So Lagrange had this idea of generalized positions and generalized velocities that he introduced in the late 18th century. And so in this context, for example, if you calculate partial L, partial theta dot, what this means is actually angular momentum. Whereas if you were to calculate partial L, partial x dot, if x was your variable, this would be linear momentum. So in this Lagrangian mechanics setup, angular physics and linear physics, it all becomes part of the same Euler-Lagrange story, the same Lagrangian physics. And you can naturally treat physics with respect to all kinds of weird geometry that would have been very difficult from like a free body force diagram perspective. Energy becomes central. This is minimizing energy is what this all comes from. But anyway, so to answer your question, I think the use of generalized coordinate systems is more tied to this story than integration per se. Integration, but that's not, I really, those are not divorced. Like integration comes up in this stuff too, so I don't know. It's hard to say. But. All right, I think I should get back to the example. I'll leave it. All right. Uh-oh. Attendance. Jeez. I had it right here too. Well, all right. There you go. Good luck finding a. You'll find it. You'll find a way. Well, you have to earn your. I mean, part of attendance is finding a place to put it. You know, I should really start the sheet on the other side of the room to make them face the thing you're facing right now. Oh, what the other class did was they wrote the names on the back, which you can see through. If you look on the back, you can actually see your name, and you could write it on the back and start columns on the back. Yeah. That's kind of a fun way. All right, anyway, you're like, you could just print out another sheet. I know, but this is more fun. So 2 pi And then something we actually have to think about. I do believe that is a minus cosine cubed phi over 3 antiderivative. Differentiate that, see if I'm right. That's right? Yay. Okay, so then we have to evaluate from, if this works out to 0, I'd be so embarrassed. It does? No. Say it isn't so. Say it isn't so. So if you plug in pi, you get cosine cubed of pi, cosine of pi cubed, cosine of pi parentheses cubed. That's minus 1 cubed, also known as minus 1. Minus 1 is 1. Long story short, upper bound evaluates to 1/3. Lower bound evaluates to minus 1/3. All said, 2/3. So, sorry. Close though. The issue is with the minus on the upper bound, actually. Yeah. Thought you did it. I'm sorry. Pretty sure. Well, hey, we'll find out soon. We're going to do this another way, and if we get the same answer, if we get 0 the other way, then we'll know you're right. Let's see here. So, or we're both wrong. Wait a minute, no. I should shut up. Okay, 4 pi over, it looks like 15, yeah? All right, now, next. 2. Let's calculate the flux directly. So I'm supposed to calculate the integral of f dot ds. All right, over the boundary of the ball. So here we've got, here we have ds is equal to, r squared sine phi d theta rho hat. But in this context, that is just sine phi d theta rho hat, because we've got, r equal to 1 for the setup here. Okay, and then the question is, what is f dot ds actually look like before I do the integration? What we're really looking at is just 1/3 z cubed z hat dot rho hat, and then I still got my sine phi d theta, right? So what's z hat dot rho hat? Well, remember rho hat is cosine theta sine phi, sine theta sine phi, cosine phi, right? So therefore, z hat dot rho hat is nothing more than cosine phi. So what this leads me to then is that the integral over the surface of the sphere, the flux of this vector field through the sphere, it's going to be the integral from 0 to pi, integral from 0 to 2 pi. And what does my f dot ds work out to in this context? Remember z, what is z equal to? Rho cosine phi, right? So what we got here? It's funny. So let me write it out symbolically. We've got 1/3 rho cubed cosine cubed phi, right? Times the cosine phi times the sine phi times the d phi times the d theta. Now, this rho here, what are we doing right now? We're doing a surface integral, right? So part of doing the surface integral is we're supposed to evaluate the vector field on the surface, right? What is rho on the surface? What is the boundary of B? It's really just where rho is equal to 1, right? So that means we just evaluate rho to be 1. Okay? In other words, you can just erase this piece right here. So we just have this integral 1/3 that stuff. Oh, it's not that bad, actually. So that gives us 2 pi, right? And then the integral from 0 to pi, well, 2 pi over 3. I'll bring the 3 out front. Looks like we got a cosine to the 4th phi sine phi d phi, yeah? And so we're looking at 2 pi over 3 minus the cosine, the 5th power of cosine of phi divided by 5, evaluated from 0 to pi. All right, let me write it out in gory detail. 2 pi over 3. So we're looking at cosine of pi to the 5th power with a minus over 5, minus parentheses, minus the cosine of 0 to the 5th power over 5. Which is equal to 2 pi over 3. That's a minus 1 to the 5th power, which is still minus 1. Minus minus gives me 1/5. And that's also plus 1/5. So we get ourselves a 4 pi over 15. Yay. So, yep. Phew. I was worried there. What if Gauss's theorem was no longer true, right? What if one day you go to your Calculus 3 test, and you just happen to come to the Calculus 3 test that one day that the divergence theorem stops being true? Wouldn't that be annoying? Like you'd have to calculate all the fluxes directly from the definition. It'd be such a drag. Enter it as a paper. Yeah, you could. That is true. You could write a paper. If that was to happen, you could definitely write a paper about that. Because it would mean you're working in some sort of universe where standard logic had been replaced with some sort of non-standard logic, which would be quite historic, really. Ignoring presidential elections, but see, the beauty of that comment is I don't have to edit it, because you could take it either way, right? If you're a Democrat, you're happy with the comment. If you're a Republican, you're happy with the comment. Everyone's happy with the comment, pretty much, right? Except for those people who feel dogmatically that our presidential elections have selected the best leaders in the recent past. I'm really happy about it. I need no such people. So anyway. Oh, now I'm working on editing it. Yeah. All right, I stopped. So by the way, this is an advertisement for linear algebra. So in linear algebra today, we learned that if you were studying this horrible formula, 1 equals to 2x squared plus 2y squared plus 5z squared plus 4xy minus 2xz minus 2yz. This is actually a tilted elliptical cylinder in disguise. Now, is this on your list of standard examples in this course? It is not. If I cover up these terms, though, it is, right? You can tell that would be an ellipsoid, right? But when you have these cross terms, you guys just don't have the technology yet mathematically to handle these things, except to put it into Mathematica and just look at it, right? The point is, if you learn about something called eigenvectors, they will reveal new special system of coordinates called eigencoordinates. With respect to the eigencoordinates, it reveals the principal axes of symmetry of the solution set to this. And so just from looking at the eigenvalues alone, you can decide whether or not you're looking at an ellipsoid or a hyperboloid or whatever. And but anyway, so if you take Math 221, I think Dr. Smith sometimes gets to this stuff. I always make a point of getting to it in 321 towards the end. But even if you don't get to it, it's in the linear algebra book. You can read it. Yeah.
We're doing it right now.
Oh, good. So this is why eigenvalues are very, very interesting, because they reveal special coordinate systems where formulas decouple into their most simple form. Yeah. Anyway, obviously not on the test for you guys. Unless you also are taking my linear algebra. Are you? Is there one person who? Ah, yes. Who else? Wasn't there someone else who taking linear as well? No? Okay. You had there was someone else doing it, but maybe they changed. I forget. somebody has a conversation with me early in the semester about doing something, whether or not it's actually done, it becomes a reality in my mind. So I forget people make decisions and change their plans and so forth. Anyway, all right. So next topic here. Well, more of the same topic, really. An example, a disturbing example I want to share with you. The Coulomb field, F, equals to, let's say, rho hat over rho squared. In Cartesian coordinates, this looks like the vector field x, y, z divided by x squared plus y squared plus z squared to the 3/2 power. All right? This field. It's the inverse square law. Spherical. If you were to picture it, it just emanates out from the origin in all directions, spherically symmetric, and its magnitude drops off as the square of the distance from the origin. This is how gravity behaves. This is how the electric field from a charge behaves. It's the inverse square law. Important vector field. So we could calculate the flux of this through a sphere, right? In fact, that was my first example. I'll remind you, though. If we calculate, to say, the boundary of the ball of radius r of f dot ds, this is most lazy to do if we use the spherical coordinates frame. Let's do it. 0 to pi, 0 to 2 pi. My f is rho hat over r squared. See, f evaluated at this. What is the formula for this? The formula for this is rho equals to r. Theta and phi are free. So when I evaluate the vector field at the surface, and I'm using spherical coordinates, all I got to do is just set rho equal to r. That is it. That is what evaluation of the vector field looks like in spherical coordinates. Isn't that nice? Doesn't that beat the pants off thinking of this as f of x, y, z? And I have to think about f of r cosine theta sine phi, r sine theta sine phi, r cosine phi. That's what I'd have to do if I was working with our direct definition as in terms of parameterizations, in terms of the spherical angles. I'd actually have to plug in, this is x, this is y, this is z. After a bunch of arithmetic, it eventually would simplify down to this, essentially. Although it wouldn't look like it. Anyway, then I don't think I did it this way the first time we did this. So right now what's ds? ds, remember, is rho hat r squared sine phi d phi d theta. There's the spherical volume element, which is also in the rho hat direction. So rho hat dot rho hat is 1. I think when I did this in class before, I actually did it more from the definition, and we had to do a bunch of trigonometry. All right? So I'm showing you like the laziest way to do this calculation right now. Rho hat dot rho hat is 1. The r squareds cancel. We're just left with the integral from 0 to 2 pi. The integral from 0 to pi of what? Sine phi d theta, which, by the way, is the integral from 0 to 2 pi of d theta times the integral from 0 to pi of sine phi d phi. After you see this about the 4th time in this course, you should probably start to notice that the integral of sine from 0 to pi is 2. So you get 4 pi. Okay? Great. So the flux is 4 pi. We got 4 pi k when I did this before because I multiplied this vector field by k, where k was a constant. Okay, what about Green's theorem? Divergence theorem. Calculate the divergence of this vector field. What's the divergence of f? I'll try to look, if we have time today, I'll try to look up in my notes and show you where the formulas are for spherical divergence. No one emailed me to ask for the page number, so I didn't send it. Yeah, it's fine. You guys have other things to do, I understand. I mean, I heard about the Thor Ragnarok and the Black Panther showing out in the lawn this weekend. I must admit, I'm tempted. No? Am I wrong?
Wait, is that this weekend?
I think it's just, yeah, Saturday. 8 till the wee hours of the morning, yeah. I wonder if it's going to rain. Anyway, this calculation we did a while ago in the two-dimensional case, I mean, anyway, through pretty much the same calculation, this works out to 0. That's either a straightforward but laborious calculation in Cartesian coordinates or a really stupid calculation if we've got the spherical divergence formula sitting in front of us. The spherical divergence formula, it's got stuff like partial theta stuff, partial phi stuff. There's stuff here, there's stuff, I don't remember exactly. But finally, there's partial phi, and you end up with like rho squared times the rho component of f. So for this stupid vector field, the f rho component is rho squared, and so this thing just becomes 1. And these are functions of just rho, so this is automatically 0, this is automatically 0, this is a derivative of a constant, so it all works out to 0. It's like one line if you already had the formula in spherical coordinates. It's really, really easy to see. So we anyway, or you can work out partial x of this, plus partial y of this, plus partial z of this. There's a conspiracy of subtraction that ends up making it work out to like 3 rho squared minus 3 rho squared being 0. Anyway, you can check this. What does the divergence theorem say then? Oh no, this is embarrassing. If we do the triple integral over the ball radius r of the divergence of f, the divergence theorem says that that's the integral over the surface of the ball of f dot ds. We just worked out that was 4 pi, right? But I'm telling you, you can work it out, that divergence is 0. Oh man, this is embarrassing, isn't it? Look at that. So we've got 0 equals 4 pi. But we have a hole. So you recognize this example as the 3-dimensional version of the 2-dimensional discussion we had before. I showed you a similar example in 2 dimensions where it seems to contradict Green's theorem, but actually the issue is that there's a place in the domain. I said the divergence is 0, but a more complete answer to this is it's 0 where rho is not equal to 0, and it's just undefined for rho equal to 0. That's the truth. It's not really 0 everywhere. There's a place, there's a singularity here. And so for times like this, we need divergence theorem with a hole. All right, or you could say the holy divergence theorem. It's here. No, don't say that. So suppose you've got like a sphere, because I can draw those. If you take it and you cut it like so, all right. And then if you can imagine cutting a hole in the middle of the sphere, I mean, this isn't, I guess it should all be dotted. It's inside the thing, you know. So here's an actual edge to the bottom of the hole. Here's a side view of what's going on. Oh, duh. It's right here. So if I just draw a two-dimensional picture of this, I'm saying there is a hole. So I want to think about my region being this between the inside purple edge and the outside black edge. I'm thinking of like a hollow gumball or something, right? There is a divergence theorem for such things. All right? And it's very simple. It's just this. The integral over the volume B of the divergence of the vector field is equal to the surface integral over the boundary of B of the vector field, the flux through the boundary. But the thing is, the boundary of B, this is where it gets sneaky. The boundary of B is the outer unioned with the inner. So let me be more specific here. Maybe it's better. Tell you what, let me, well, okay, so if I can, it's easy for me to draw over here. This is the normal of the outer part. So this is S out. This is S in. Right? The inner edge of the boundary of the solid, the outer edge. And so I'm saying that the outer edge is oriented. So here's the way positive orientation works for solids. The normal has to point outside of the solid. So the positive orientation of the inside surface points inward. So Sn has like this. And so it's just the surface analog of the fact that holes, to positively oriented holes, we need clockwise oriented holes, whereas we needed a counterclockwise oriented outer edge. In the same sense, for a volume, we need an outward oriented outer edge, but an inward oriented if we have holes, surface to any hole inside the solid. But with that convention, this, all right, so now, but just to be annoying, suppose we use a different system of labeling. Suppose we had this was S1 and this was S2, right? And here's and suppose that they're both oriented outward like that. So then if this is my B, the boundary of B would be the S1, excuse me, S2, good grief, S2 union with not S1, but the boundary of B by definition is minus S1. All right? If I want to think about an outward, if I want to think about the normal to S1 going in some sense in the same sense as S2 for the purpose of comparing the flux through S1 to the flux through S2, I would think about that. And with respect to that, I would have the integral of the divergence of the vector field over the volume of the ball is equal to what? It's equal to the integral over S2, the flux through S2, right? Minus the flux through S1. So if the divergence is 0 between your surfaces, what does this tell us? It tells us that the flux does not change as you expand surface 1 into surface 2. The same number of field lines piercing 1 also pierce 2. There's no new field lines created between these surfaces. That's what the divergence being 0 means. No new diverging field lines. And this is another example of a deformation theorem. So I just showed you that the flux of the Coulomb field through a ball of radius r is 4 pi, right? So imagine in this example that maybe, the thing is I drew this picture for S1 and S2 pretty, but, you know, it could be much uglier. You know, you could have, something like, you know, some kind of blah. And here's the origin, right? And you could ask, for that F that we're talking about over there, the Coulomb field, what's the flux of F through that surface? Outward oriented, of course. And the answer would be? The answer would be 4 pi. And the reason for that is because I can take inside my surface, I can stick a sphere inside there, right? And I know for a sphere of radius r, I know the flux through the sphere is 4 pi. We calculated it over there. And so by the deformation theorem, because the divergence, again, keep in mind, I'm talking about that specific vector field, the rho hat over rho squared vector field right now. Same flux, goes through this, it goes through that, so it's 4 pi. Now, I haven't proved this yet. How do you actually prove this result? That's what this picture was about, guys. I was showing you how we prove it. See, because the point is, you can take the ball, right? And you got, like, let's say B north and B south, right? You have the intelligent part of the sphere. You have the equally intelligent part of the sphere. See, now I'm really working on editing this. Sorry, there's no north-south humor allowed in here. Are you guys Northerners or Southerners, actually? I have no idea. You any Canadians in here? Midwesterners?
I still don't know who Hawaiians are.
Hawaiian, definitely an outlier. Let's see here. That's a good question. How did Hawaii fare in the Civil War?
Several Hawaiian captains in the Hawaiian military actually fought for the North.
Ah,
Yes.
so you're Northerners then. All right.
But we're not Yankees.
You're not Yankees. Anyway, the larger point here is if you look at, you chop this hollow sphere into two pieces, what can you say about the north piece and the south piece? They're simple solids. There's no holes in their interior. So you can apply the ordinary divergence theorem on each half separately, and when you do and add the results together, you get the outer edge, you get the inward oriented inner edges, and the place where it's cut cancels out. This part would be like that way, and on the upper half it would be the other way. So like if I draw it over here, the cutting looks like this. And so the this would be down, and the same surface but oppositely oriented would be up. So when you add those fluxes, they cancel, and outward oriented for the bottom looks like this, right? But outward oriented for the top looks like what? Right? And so that's how you get this conspiracy of inward orientation of the inside and outward of the outside. That's where this notion of, well, that's how the notion of positive orientation for surfaces works together to make the divergence theorem still make sense for stuff with holes. It's pretty neat that this rather simple system of orientation allows us to extend theorem to things with holes. So, anyway. So, one parting thought as it relates to this. In physics, you learn this, the divergence of this vector field, rho hat, over rho squared, is actually equal to 4 pi, the Dirac delta function, the three-dimensional Dirac delta function of well, we don't, in physics we wouldn't use this silly rho hat notation. We'd use r hat over r squared, actually, because r squared is the typical notation for spherical radius in physics, and this would just be r vector. This is the so-called Dirac delta. three-dimensional Dirac delta. It's got the very curious property that if you integrate a function of x, y, z times the delta function, delta 3 function of x, y, z dv over some volume, it's equal to f of 0, 0, 0, provided that this volume includes the origin somewhere. This is a really weird thing. I'm saying that you integrate the Dirac delta function. If it includes that one point, the origin, it gives you something finite. Otherwise, actually it's 0. But this is the mathematics of a point charge. The density, the charge density of a point charge is given by a Dirac delta function. And I really should put function in quotes because it's not a function. This is nonsensical in terms of ordinary calculus. You can't integrate a continuous function in some way such that one point gives you a finite value, right? It's not how integration works. So in fact, the Dirac delta function is an example of something called a distribution. And the mathematics of this was worked out in the early 20th century by a mathematician named Schwarz. Dirac was a physicist. If you take the junior level electricity and magnetism course, these are sprinkled all throughout because we like to think about point charges and point currents, localized charges and currents. And localized charges and currents are written elegantly and succinctly in terms of Dirac delta functions. But anyway, we also talk about Dirac delta functions a little bit in differential equations because there's a good reason to do that there as well, but not these kind. The kind that are like one-dimensional. All right, with that, let me ask you if you have any questions about the homework. And while you're thinking of your question, I will be trying my best to find the formulas I was talking to you about in terms of the curl and divergence and spherical coordinates. So I'm hoping to get a bunch more daily quizzes in Friday. Let's see here. Where's my old stuff? Man, don't I have a link to my old stuff in here? Yep.
I had emailed you about the test for.
Oh yeah, that's lost. I don't know where that is. Sorry to say. It's essentially gone. I mean, here's the old, the archives, as I call it. Might find something in here. What's old test 3 look like? Oh, no, still the, still looks all integrate-y. This one might be relevant. This is the, let's see here. This one actually is relevant. So, but it's take home, of course. So yeah. Ooh, see, I was actually teaching them Euler-Lagrange equations. Check that out, yo. All right. But if you look at the do you know where how I got to this, guys? At the top of your web page, it says Multivariate Calculus Archive right under the zoo. Click on that. It takes you to a page with more older stuff. And this week, I was just showing you solution from test 3 from spring 2009. That was the content of this course, but in 3 hours. That happened 1 year. That was so much worse than what we're doing. I did not realize what had been done to me when I was asked to teach that.
3 hours a week?
Yes, it was truly horrible. Anyway, Here we go. This one right here, guys, is one I should send you a link to. So in this PDF, which I should probably, did you resize it? Because I always forget to do this. Ah. There we go. It's cool. I derive what the curl and divergence look like in other coordinate systems after a bunch of chain rules and calculus and junk. This is the divergence formula for the divergence in cylindrical coordinates. It's a little bit surprising, isn't it, that you pick up an r in the z term like that. Well, there's one over r here. Or you could write it like that. All right, so that's the divergence in in cylindrical coordinates. It's takes me about an hour of lecture to derive the divergence in spherical coordinates. It looks like that. There it is in all of its glory. The formula I was mentioning. Which is kind of surprising, right? Like the divergence in Cartesian, partial p partial x plus partial q partial y plus partial r partial z, somehow changes into this when you change coordinates. So my point was for this vector field, for the Coulomb field, that's 0, so both of these terms are gone. And this right here, f sub rho, is 1 over rho squared. So this just becomes 1, and the divergence is just obviously 0 with this formula in hand. It's actually about a half a page of differentiation if you use Cartesians, yeah? As bad as that is, calculating the curl, there's the curl in cylindricals, yay. And behold, the curl in, well, no, not yet. Premature. Here is a table I stole, I think, from Thomas's calculus, or possibly from Griffith's, I forget. Yeah, oh yeah, this is Thomas's. You can tell it's a calculus book if it's using rho. Physics will not use rho as a spherical radius because it's dumb. I do it because of groupthink, peer pressure, whatever. Anyway, here's the formulas for everything. And by the way, these are called the Laplacian. The Laplacian is also quite different in cylindrical versus spherical compared to Cartesian. It's nice, right? Cylindrical, spherical, Here's what they look like. Here in physics, here's the dictionary. Math, we use rho. Physics tends to use r. Math uses theta. Physics and engineering tends to use phi in the place of theta. And just to make things extra fun, math uses phi, physics uses theta in the place of phi. And then, of course, not being content to further confuse, we use r, and physics tends to replace that with s for the cylindrical radius. What's that? Well, yeah, here's formulas for all the. Here's the x hat, y hat, z hat in terms of the spherical frame, and here's the spherical frame in terms of the Cartesian frame, cylindrical frame in terms of, here's conversions back and forth from frame to frame. These formulas are super convenient if you actually find yourself doing some serious calculus, vector calculus that involves curved linear coordinate systems. This is something you should know about. So I'll send you this link. Anyway, I wanted to talk to you about this for a minute. Do you guys have questions about your homework in the minute that remains? If I can find it. 119 and 120. I'll just do that in the minute that remains. Which one? So you said again it was mission. Sure, why not? Which one we asked about? What? 119? Oh no, I have no solution for that one. Sorry. Seemed hopeful. Guess I better write a solution for that, huh? Thanks for reminding me. Ay, where did it go? I'm sorry, guys. I'll find it eventually. Problem, what was it? Yeah, well, this is a graph. It's a graph. F of xy is equal to 4 minus x squared minus y squared. Its domain, it's bounded below by the xy plane. So it's a paraboloid that opens down. It hits the xy plane at a disk of radius 2 by my estimation. Because if I put that equal to 0, I get 4 is equal to x squared plus y squared. So I think that the domain would be x squared plus y squared less than or equal to 4. I would use polar coordinates to actually calculate the integral after push came to shove. So I would set it up perhaps as a graph. Alternatively, you could parameterize the paraboloid using, x equals to r cosine theta, y equals to r sine theta, and let r range from 0 to 2 and theta range from 0 to 2 pi. That'd be a parameterization of the paraboloid that would work out pretty nice for you. I'm not sure what your question is. Didn't know where to start. I would say think of it as a graph. We have laid a path down through the wilderness how to calculate the surface integral of a graph with respect to, and then this one here. So ds is what? ds is r squared sine phi d phi d theta, right? So to do this integral, you need to change r to spherical coordinates. This little r would be what? It would be r sine phi, right? Little r is r sine phi when rho is equal to r. So to do this, you basically need to integrate sigma, which is a constant, right? Is constant, right? Yeah, constant. And I think what I'm seeing is I would get r to the 4th, I want to say sine cube, sine cubed of phi times d phi d theta, phi integrated from 0 to pi, theta integrated from 0 to 2 pi. In short, this ds we've calculated before in the notes, right? So what I'm talking about, you guys, is the fact that I've shared with you guys these, standard examples just to make sure I'm not talking past you. You have another class to go to? Yeah. I don't know if this is more important, but my point to you would be on page 358, I have the ds that I'm talking about, okay? And then for the other one you asked me about, 119, if you look ahead, the graph right here, number 5, that shows you how to set up that kind of integral. I mean, you can do it like that. All right, I shut up. See you guys tomorrow.